the last session, but I needed it with a sense of completeness, because it's, well, this is the highlight of the whole course, and even the highlight of the whole subject of the theory of computation. The proof of the holding problem, so famous. Right. So we're now in a position we can actually prove theorem 4.11. That's on page 176 of your text. This is just a repeat. So now here's the language that we will show is not decidable. So A suffix tm, and the members of this language are ordered pairs. M is a Turing machine, and W is just a string, goes as input to the Turing machine M, and this ordered pair belongs to the language if this machine accepts this string. Right? This Turing machine M accepts this string. Okay? Now we have to, well, the task is, the theorem is, this language, A suffix tm, is undecidable. It cannot be decided. Okay? And what that means is there is no Turing machine that decides it. A bit of revision. And what is it to decide language again? At the risk of boring you crazy, you've heard it so many times, but reinforcement can be useful. What is it to decide language? It means there's some Turing machine that accepts every string in the language and rejects all other strings. That's what decide means. Okay? So how to prove that this is undecidable? Well, we're going to use proof by contradiction. Okay? Now, steadfast method of proof. I've used it a lot. And so, as usual, in a proof by contradiction, you assume the opposite. You start with the opposite of what you really want to prove. And what we really want to prove is this is undecidable. Undecidable. So the opposite of that is that it's undecidable. In other words, decidable. Okay? So we will assume that this is decidable. Now what does that mean? Well, that means there's some Turing machine that decides it. Okay? So let's call that Turing machine H. H for halt. Right? It's the halter. The Turing machine that halts. And so this Turing machine H will be a decider. Okay? By definition, because we're assuming this language is decidable. By definition, that means there is some decider, some Turing machine that decides the language. Okay, so we'll assume H is a decider for this language, so that H is a decider for that. And we will, through quite a few steps, it's quite an elaborate, detailed proof. You need to concentrate step by step by step by step, quite a few steps. We will deduce a contradiction. Quite a crazy contradiction, in fact. Something really weird starts happening, and highly ingenious. And I can't really say Turing did it this way. I don't think he did it quite that way at all, because he used his UTM, his universal Turing machine, which is a Turing machine capable of simulating any other Turing machine. Okay. And he got his famous halting problem proof from considering the UTM, universal Turing machine. Okay, now let's see. So we'll just go through the analysis step by step. And how many? So it's 1, 2, 3. Three whole sessions just on this proof 4.11, and the last just a little bit more than the last session, is effectively showing the existence of a language that is not even Turing recognizable. So Turing machine's even more impotent with such a language. Okay, so alright, so we assume this is decidable, therefore a Turing machine decides it. Let's call it H. So what does H actually do? So it has, by definition, it's a decider, right? So it has to accept every element, every member, every string in other words, of this language. So it takes this string. Now remember, it is a string because the angular brackets implies that it's an encoding or a representation of two things: one, the machine, and two, the string. So that encoding, that information about those two things, is put into string form. So this is a string, and a language is just a set of strings. Okay. So this Turing machine H will look at this string, and it will have to accept it if this string belongs to this language. And any other string, the Turing machine will reject. Okay, because by definition, this Turing machine H is a decider, and that's what deciders do. They accept all strings belonging to the language, and they reject all other strings. Okay. All right. So now, if this ordered pair is in the language, then by definition, this machine, whatever this Turing machine is, M, it will accept W. Right? So H will accept this string. Think about it. Now it's starting to pay attention. H will accept this string if M accepts W. Make sense? See, if M accepts W, then it's a member of this language. Okay? But if H is to decide this language, it has to accept this string. And so H accepts this string if M accepts W. Okay, hope you follow that. If not, rewind. Let's see. So H accepts and halts, of course. Well, it's basic definition of a Turing machine, right? There's two ways a Turing machine, again, a bit of revision. There's two ways a Turing machine can halt: by accepting or by rejecting. And if it doesn't halt, by definition, it loops, like just never halts, just goes on forever. It's called looping. Right? So there are effectively three things a Turing machine can do. It can accept, reject, or loop, or two, in a sense, only two things it does. It can halt, or it can loop. In other words, it can halt or not halt. Okay. Now H will reject, and of course halt, if this M fails to accept W. Right? Because if M fails to accept W, well, this ordered pair is not in the language. Right? It's only in the language if this machine, whatever it is, M, Turing machine, accepts W. Right? It's the condition, that's the property that the ordered pair, the string, has to be a member of the language, by definition. Alright, so we can say if this is the input string to this machine, H, the decider, and it's an ordered pair, it's in string format, an encoding representation of the information about two things, the machine, the Turing machine, and the string. Okay, so as input, H acts on this string, and its decision, its output, will be accept if M accepts W, and it'll be reject if M does not accept W.